Welcome back to the Pro Ticker Deep Dive. Today we are taking a monumental journey into the infrastructure that underpins, well, pretty much the entire digital age, semiconductors.
Yeah, it's a huge topic.
It really is.
Mm.
And you often hear that specialized silicon is the new oil, right? Powering everything from your smartphone to the world's fastest supercomputers.
Mm-hmm.
But this deep dive isn't just about how important chips are. It's about this massive, really unprecedented collision that's happening in the industry right now.
That collision is, it's defined by two huge forces pushing against each other. On one side, you have this utterly explosive, just generational demand.
From AI.
Entirely from generative AI, large language models, machine learning. The demand seems insatiable. I mean, cloud providers are ordering high-end chips by the tens of thousands, sometimes hundreds of thousands.
Oh, okay, so that's one side. What's the other?
The other side is you find these acute supply bottlenecks, and in really unexpected places, I might add. All of that is wrapped up in this colossal geopolitical restructuring.
Which is mainly the U.S. and China.
Primarily fueled by that strategic fracturing between the U.S. and China, yes.
So our sources for this give us a really phenomenal, comprehensive, full-stack analysis of this world. They map the whole value chain, starting literally from the raw silicon sand all the way up to the finished systems that, run our world.
Right.
So our mission today is to take you through this map, identify the precise pressure points that are holding up the AI boom, and maybe most importantly, understand the technological and policy shifts that are going to define the next decade of computing.
And to navigate all that complexity, we've broken the industry down. We'll start by mapping the 6 essential segments of the semiconductor full stack, just to show how specialized this whole ecosystem is.
Okay.
Then we'll zoom in on the acute choke points, which right now are memory and advanced packaging. That's where the immediate friction is.
Got it.
After that, we'll get into that seismic geopolitical realignment being forced by the U.S.-China competition. And then finally, we'll look ahead to the long-term future. What happens when Moore's Law, as we've known it for 50 years, fundamentally changes?
All right, let's unpack this full stack then. It's way too simple to just think chips. This is a chain of intensely specialized, globally connected operations. So we're starting at the top, the brains of the operation. Logic chip design.
Logic chip design. Yeah, this is the segment where your CPUs, your GPUs, your complex systems on chip, or SARCs, are all conceived and specified. It's the high-performance heart of all modern computing. It's all about processing power and efficiency.
And this space has been dominated by a few giants, but they have slightly different business models, right?
Precisely. You have the fabulous design firms like NVIDIA and AMD. They design the intellectual property, but they outsource all the manufacturing to foundries like TSMC.
Okay, so they don't actually make anything physical.
Not a single chip. And then you have the integrated device manufacturers, the IDMs, most famously Intel, which historically designed and fabricated their own chips, though that model is changing really fast now.
And the battleground today is all about what? The smallest, fastest chips?
It's intensely focused on 2 factors. One is the most cutting-edge process nodes. We're talking 5 nanometer, 3 nanometer. And the other is the rise of advanced chiplet architectures.
Like AMD's multi-die designs.
Exactly like that.
Let's focus on those chiplets for a second. Why are they becoming so important all of a sudden? Is this a structural shift?
It is, and it's a matter of physics and economics. As you shrink below 7 nanometers, the cost to manufacture one single huge piece of silicon on a monolithic chip, it becomes prohibitively expensive.
You get diminishing returns.
You do, and your yield, the percentage of working chips you get from a wafer, it just drops dramatically. So chiplets solve this by breaking that big processor into smaller specialized tiles.
So a little piece for memory control, another for the CPU
Well,
cores.
exactly. A memory controller here, a CPU core block there, an I/O block, and then you connect them all together with these ultra high-speed interfaces in the packaging stage. It improves yield, lets you mix and match, and it fundamentally lowers the cost.
That makes a ton of sense. Now let's talk about demand, because the sources are highlighting a complete bifurcation here.
The contrast is really stark. The pandemic-era spike in demand for standard PC and smartphone CPUs, that cooled off cyclically in 2022 and 2023.
Right.
But that cooling is just utterly dwarfed by the vertical explosion in data center GPU demand. Generative AI workloads need this unprecedented parallel processing power.
And the sources say the cloud providers are ordering tens of thousands of advanced AI chips.
Tens of thousands. The NVIDIA A100s and H100s are the specific examples, and that has fueled this massive structural and frankly unbelievable revenue growth for the big AI players, most famously NVIDIA.
And it's not just the volume. This demand has also changed who is doing the designing. We're not just relying on the old guard anymore.
That is the crucial long-term trend. We're seeing the rise of custom silicon. Domain-specific architectures. Think of Apple's M-series chips.
Which totally transformed the Mac.
Exactly. They transform performance by tailoring the silicon perfectly to their software. Or you have Amazon's Graviton processors designed specifically for their own server workloads.
So more big companies, Google, Tesla, are designing their own chips now.
Right. And this fragments the market share away from the traditional suppliers over time, but it has a huge positive structural effect on the EDA tool segment, which we'll get to in a bit.
It's basically saying that hardware has become the differentiator for software. If you want a real edge in AI, you have to control the silicon yourself.
That's it exactly. And that control starts right here in the design phase.
Okay, so holding that thought, let's move to segment 2, memory. If logic design is the brains, memory is the immediate short-term headache. This is where the industry has just run headfirst into a wall.
Memory is absolutely the new critical bottleneck, and the data on the supply crunch is just staggering. This segment, it covers your standard DRAM, NAND flash storage, and the ultra-high-performance HBM, or high-bandwidth memory.
And it's basically an oligopoly, right?
A very consolidated one. Samsung, SK Hynix, and Micron. Together, they dominate well over 90% of the DRAM market.
What's so fascinating is how quickly this market just completely flipped. Memory is known for these brutal, deep, cyclical swings.
And that's the key context. We just came out of a painful glut, oversupply, a price crash through 2022 and early 2023. Investors were super cautious.
But then it turned.
It turned violently, almost vertically, in the first half of 2024. And the reason? The AI frenzy. AI servers aren't just powerful, they are memory hungry. They need massive amounts of the highest performance memory out there, specifically HBM3 and high-speed DDR5.
And it's not just about how much memory, it's about the unique role that HBM plays.
It's the sheer bandwidth. Traditional memory is physically far from the processor, which limits how fast you can move data. HBM stacks multiple DRAM dies vertically and integrates them right next to the GPU inside the package,
Which allows for way faster data transfer.
astronomical increases in bandwidth. We're talking 10 to 15 times faster than standard DDR5, and that's essential for feeding those hungry AI processors. You can't run a huge language model if you can't feed it data fast enough.
So what does the data tell us about how severe this crunch is?
It's extreme. Contract prices for some standard DRAM chips more than doubled in 2023 alone. Inventory levels, which the industry likes to keep around, say, 12 to 15 weeks for safety,
Yeah.
they've plummeted. Projections show them hitting a critical 2 to 4 weeks by the end of 2024. It's just an extraordinary demand environment.
That's basically running on empty. What are the memory makers saying about their backlogs?
They're years long. SK Hynix and Samsung have reportedly pre-sold nearly all their advanced HBM output for the next 2 years. SK Hynix specifically said they expect the shortfall to persist through late 2027.
Wow, late 2027. That's a 3-year plus shortage visibility.
It is. It just speaks volumes about the scale of AI investment happening globally.
But hang on, why the disconnect? If inventories are critical now, by late 2025, shouldn't new capacity ease the pressure? Why are they saying 2027?
That's the crucial question. It's because the technology is so complex to manufacture. HBM requires these advanced techniques like through-silicon vias or TSVs to connect the stacked chips. They are incredibly difficult to get high yields on.
So it's just slow to ramp up.
It's much slower to ramp up than standard DRAM, and at the same time, the demand forecasts for AI just keep compounding every single year. Every new AI server needs 6 to 8 times the HBM of its predecessor.
To put that demand into perspective, one of our sources mentioned an internal target from OpenAI. What does that tell us?
It's terrifying in its scale. OpenAI's internal 2029 target for its AI cluster would require up to 900,000 wafers per month of chips.
Which is what?
That's roughly twice the current global HBM production capacity. Now, that's an ambitious goal, for sure, but it illustrates that AI isn't just absorbing existing supply, it's demanding a completely new scale of manufacturing that the industry simply hasn't built yet.
So what does this huge demand for HBM and DDR5 mean for the rest of the memory market, the older stuff?
It creates this challenging dual bind. The memory makers are, naturally pivoting to the higher margin products, HBM and DDR5. They're reallocating factory capacity away from older, lower margin products like DDR4.
Viewed as a great business decision for them?
Hugely profitable for them, but it's ironically causing structural shortages in legacy memory products as well. The stuff needed for cars, industrial systems, older servers, they're prioritizing the massive revenue from AI.
So for now, the memory giants, Micron, SK Hynix, Samsung, they're in a sweet spot where they have pricing power in what's usually a commodity segment.
Absolutely, they are huge beneficiaries right now, but we
Yeah.
have to remember, cyclicality is the historical rule. The risk of an overbuild cycle returning around 2027-28 is real if everyone ramps up at the same time.
Okay, moving on. Let's look at segment 3, electronic design automation, or EDA tools. If you're going to build something this complex, you need some seriously sophisticated software.
EDA is the foundational software layer. It's these specialized software and intellectual property libraries used to design and verify all these chips. It's a highly consolidated niche, basically a duopoly dominated by Synopsys and Cadence design systems.
They're the picks and shovels of the chip gold rush.
That's the perfect term for them. They profit regardless of which specific chip design ultimately wins.
And we're talking about chips with hundreds of billions of transistors now.
Yeah.
So these tools aren't just useful, they're indispensable.
Indispensable is the understatement of the decade. The complexity is exploding. Without advanced EDA software, just verifying the design, let alone optimizing its layout and power, would be impossible. The tools themselves now use machine learning.
Right, like Synopsys's DSO.ai.
Exactly, which automates the optimization of complex chip floor plans. It does in hours what used to take teams of human engineers weeks.
And that indispensable nature gives this segment a unique moat. What makes them so robust, even if chip sales slow down?
Two main factors. First, their software licenses are for long-term R&D, which is planned years ahead, so they're kind of insulated from short-term dips in chip sales. Second, their growth drivers are compounding. All that design activity we talked about, new AI accelerators, custom silicon from Amazon, Google, Tesla, that ensures steady growth. Analysts project 10–15% annual growth.
And their strategic value is basically confirmed by government policy, right?
Absolutely. The geopolitical friction confirms their position as a technological choke point. Advanced EDA tools are a core focus of U.S. export controls. They're restricted from being sold to China.
Because China can't just build its own.
Not realistically, no. The technology is so specialized and complex, it would take them years, maybe decades, to replicate it. So that restriction just reinforces the pricing power of the duopoly.
Okay, segment 4 brings us into the fab itself, lithography and equipment. This is the heart of physical manufacturing, and it's probably the most capital-intensive segment in the world.
This segment covers all the specialized machinery for etching, for deposition, for metrology, which is measurement, and most critically for lithography. And here, ASML of the Netherlands holds a near monopoly on the cutting edge.
They're the only ones who can make the EUV machines.
They are the sole supplier of extreme ultraviolet or EUV lithography machines. Each one costs around $180 million and is essential for producing any chip under 7 nanometers.
And the other big players.
Applied Materials, Lam Research, and Tokyo Electron are critical for all the other fabrication steps.
The demand for all this equipment is fueling what analysts are calling a CapEx supercycle. Why so much spending right now?
It's entirely driven by government policy and that push for geographic diversification. The U.S. GPS Act, similar programs in the EU, Japan, Korea, all of that translates directly into multi-year orders for these equipment makers.
So governments are essentially paying companies like TSMC and Intel to build new factories.
And those factories need to be filled with machines from ASML, Applied Materials, and Lam Research. Global fab equipment spending topped $100 billion a year in 2021 and 2022, and it's expected to stay incredibly high for years. ASML has a huge backlog.
We're already hitting the limits of the current EUV machines. What's the next big leap in lithography?
That would be the transition to high-NA EUV with a numerical aperture of 0.55. These are the next generation machines needed to push to sub-2 nanometer nodes by 2025-2026. ASML shipped the first modules to Intel late last year.
And what does High-NA actually do that current EUV can't?
It simplifies the process. Current EUV still requires some tricks to get the smallest features, sometimes called multi-patterning. High-NA is designed to enable single exposure patterning at the 2 nanometer and 1.4 millimeter nodes. It dramatically improves yield and precision at that atomic scale.
But the cost sounds insane. If standard EUV is $180 million, these high-NA machines are what, $300 to $400 million each?
That's the range. It is economic madness, but it's technologically necessary if you want to be on the absolute cutting edge. And here's the critical point tied to that cost. It reinforces that the era of cheap Moore's law scaling is definitively over.
What do you mean by that?
For decades, every time you shrunk a transistor, you increased density and you reduced the cost per function. That's changing. Our sources have stark data on this. TSMC's pricing for its 2 nanometer node is projected to jump by about 50% compared to 3 nanometer.
From $20,000 to $30,000 a wafer.
Roughly, yes. And that increase is driven by the sheer complexity and the cost of the equipment, like high NA EUV. It means, and this is a huge deal, for the first time, cost per transistor will rise rather than fall.
So the leading edge is now only for a handful of giant companies who can afford it.
That's right. TSMC, Samsung, and Intel. That's pretty much the list. It makes the equipment segment a crucial choke point, both technologically and financially.
Okay, moving to segment 5, we arrive at what is arguably the most acute bottleneck in the entire value chain right now. Advanced packaging and assembly. This used to be the boring back-end part.
The shift is radical. Packaging is no longer a low-margin assembly job. It's a critical frontier of innovation. Advanced techniques, like TSMC's CoWoS or Intel's Foveros, let you integrate multiple chiplets, a logic core plus HBM memory with ultra-high density.
And this is how the industry is getting around the end of cheap scaling.
It's how they're extending Moore's law through integration, exactly.
So if fabricating the wafer is like baking the cake, what's advanced packaging?
It used to be like putting the cake in a box. Now it's like being a master pastry chef that has to stack 3 different incredibly complex cakes perfectly and connect them with microscopic precision. Right now, everyone has a beautiful baked cake, the wafer, but they're all waiting in line for that one specialized frosting machine.
And the demand for that frosting has exploded.
It tripled year on year by late 2023 for technologies like CoWoS. Major designers like NVIDIA and AMD are scrambling to secure packaging capacity.
The severity of this led to a really blunt assessment from TSMC's leadership.
Yes. The chairman stated, and I think this quote sums it up perfectly, "It is not the shortage of AI chips, it is the shortage of our packaging capacity."
That's a powerful statement. It means after spending billions on the most complex wafer fabrication, those $30,000 wafers are just sitting in a queue.
That's exactly the situation. The AI GPUs, the engine of the whole AI boom, are forced to wait in line to be packaged. Analysts estimate the global shortage of AI GPUs could last well into 2025. That's an 18-month backlog, simply because packaging capacity needs time to catch up.
Why did this happen? Why was this such a strategic blind spot?
Because historically, packaging was low-tech, low-margin, and outsourced. The industry was obsessed with shrinking the transistor, the front end, and they just assumed the back end would keep up.
So the investment in new fabs completely overshadowed the need to invest in integration.
It was a strategic failure to recognize that integration capability would become the new differentiator.
So what are they doing to fix this now?
Throwing money at it. TSMC is investing almost $3 billion in a new advanced packaging plant. Intel is aiming to quadruple its packaging capacity by 2025, and the OF companies, the outsourced assembly and test firms like ASC Technology and Amkor, they're rapidly expanding, seeing huge revenue jumps.
Okay, finally, segment 6. Materials and substrates, the often overlooked foundations.
These are the base layers, the silicon wafers themselves, dominated by companies like Shinetsu and Sumso. Specialized components like photomasks, high-purity gases like neon, and specialized packaging substrates. When you talk about supply chain vulnerability, this is often where the real risk is.
And we saw that vulnerability exposed very clearly with the Russia-Ukraine conflict.
A perfect case study. Ukraine supplied about half of the world's semiconductor-grade neon gas, which is essential for the lasers and the lithography machines. The war halted that output in 2022, and neon prices spiked tenfold.
How did the industry manage to stabilize that so quickly?
It was a painful, expensive process. It relied on 2 things: dramatically increasing recycling of neon from existing gas mixtures and diversifying production to other countries, mostly China and the US. The crisis was averted, but the memory of that vulnerability is a powerful force today.
What are the current materials hotspots beyond silicon?
The biggest growth area is in compound semiconductors: silicon carbide, Ca, and gallium nitride, GaN. They're booming because of the EV market, where they enable much higher efficiency. 6G is used in EV inverters, GaN is in fast chargers.
And are there any acute bottlenecks in materials right now?
Yes. Photomasks, those quartz plates with the circuit patterns, hit 100% capacity in late 2023. That caused lead times to stretch. Substrates have also seen extreme shortages periodically. Material shortages are always a leading indicator of production hiccups down the line.
Okay, so we've established the 6 pillars. Now let's shift to the massive forces that are actively fragmenting this whole supply chain: geopolitics.
Geopolitics is no longer a peripheral concern. It is the primary engine driving investment now. The strategic competition between the U.S. and China is fundamentally altering everything, driven primarily by the U.S. tech decoupling strategy.
Let's start with the main tool of that
Yeah.
strategy, the export controls from the Commerce Department.
These controls are sweeping and strategic. They have two main prongs. First, they restrict China's access to high-end AI chips, so banning NVIDIA's A100 and H100. Second, and more critically, they restrict the sale of cutting-edge fab equipment, like ASML's EUV scanners.
The goal is basically a choke point denial.
Exactly, to severely delay China's progress in advanced AI and military computing.
How has this hit the American firms that were relying on China for growth?
It created billions in lost annual revenue. NVIDIA, Lam Research, Applied Materials, they're all structurally losing market access. NVIDIA tried to get around it by creating lower speed compliant chips, the A800 and H800.
But that just starts a cat and mouse game with regulators.
It does. If the U.S. tightens the rules, those chips could be banned next.
So the strategy is to deny China the leap to the 5mm, 3nm, and 2mm nodes by controlling the essential machinery and software.
Precisely. They've identified the choke points EUV, advanced EDA, and denied access, while getting allies like the Netherlands and Japan to align their bans. It creates a unified technological wall.
Of course, China's response is this massive national mission for self-sufficiency.
No, they're not just accepting it. They're channeling enormous resources through things like the Big Fund to earn $30 billion and aggressively promoting alternatives like the open source CPU architecture RSCV.
And what does that progress look like? What can their top foundry, Semic, actually do today?
SMEC can reliably produce chips at 28 nanometers in high volume. That's good enough for cars, industrial controls, a lot of IoT stuff. There are also reports they've achieved 7mm capabilities in small volumes.
Wait, 7mm advanced. How are they doing that without EUV?
Through DUV multi-patterning, basically running the wafer through the lithography machine multiple times. It's technically possible, but it's extremely challenging, very costly, and has much higher defect rates. It's an inefficient, costly workaround.
So what's the realistic outcome for China's self-sufficiency drive?
The consensus is that China will successfully achieve a mostly self-contained supply chain for chips at 28 nanometers and above. But reaching sub-10 nanometers efficiently or catching up in advanced memory like HBM is likely a decade or more away without external access to the cutting-edge equipment.
This deadlock brings us to the third big force, the global scramble for diversification, all fueled by the immense risk around Taiwan. We're calling it the price of sovereignty.
Taiwan is the critical choke point the world cannot afford to lose. It produces about 20% of global semis, but critically, over 90% of the world's leading-edge chips. Almost all of that is from TSMC.
Which is the single largest tail risk for the entire tech industry.
Absolutely. And that risk has catalyzed this massive push for geographic diversification.
This is why we're seeing the global subsidy race, like the U.S. THES Act.
Exactly. The $52 billion CTUS Act, plus parallel initiatives in Europe and Japan, it's a massive, deliberate effort to build resilience by building fabs outside of East Asia. The SIA projects the U.S. share of advanced logic could go from basically 0 to around 28% by 2032 because of this.
But let's talk about the economics of that. What is the actual price of sovereignty?
It's significant. We're talking TSMC investing $40 billion in Arizona, Intel building mega fabs in Ohio and Germany. The crucial consequence, the price of sovereignty, is that moving production increases costs. TSMC has warned its U.S. fabs will run 20 to 30% higher costs than their Taiwan operations.
But hold on, if these new fabs are so much more expensive, how can they compete?
They won't on pure cost, but that's the point. Customers NVIDIA, Apple, AMD are increasingly willing to pay a premium for supply security. They're accepting lower efficiency for geographic redundancy. Governments are subsidizing that inefficiency because they see this as a strategic asset, not just a commercial product.
Now let's flip it. The U.S. controls the high-end equipment, but China controls some key upstream materials. What are China's counter-choke points?
China dominates the global supply of certain critical materials, most notably rare earth elements and industrial metals like gallium and germanium.
Which are essential for specialized chips.
Right, for high-frequency RF chips, telecommunications, power electronics, and China has used this leverage recently. In July 2023, they imposed export permits on gallium and germanium.
A warning shot.
It was universally interpreted as a retaliatory warning shot. While it hasn't caused a major sustained shortage yet, it introduces the risk of supply shocks for critical materials.
So the net effect of all this is a massive global bifurcation.
It's unavoidable. We're seeing the likely emergence of two distinct supply chains. One cutting-edge sphere led by the US and its allies, and a second led by China, focusing on mature tech and domestic volume. It's globally inefficient, but it ensures national security.
And it's fascinating that this geopolitical tension is the engine for that CapEx supercycle we talked about
Mhm.
earlier.
It is the single most powerful structural tailwind for the equipment and EDA sectors. Companies that occupy those choke points, like ASML, are largely insulated because their technology is essential for everyone outside of China who's trying to build resilience. Their order books are full.
We've mapped the landscape, growth, bottlenecks, and fragmentation. Now let's use the sources to guide us through the time horizon, starting with the short term, the next couple of months.
In the immediate term, we're navigating a high-speed collision. Operations are robust for AI-exposed companies, but supply frictions are incredibly tight, driving up prices and constraining delivery times.
So what are the key near-term catalysts we should be watching?
Earnings season is always critical. NVIDIA, TSMC, Micron, they'll all give updated guidance. We expect continued upbeat results, but the crucial commentary won't just be about revenue, it'll be about supply constraint duration. Is that packaging capacity ramping up faster than expected?
And we also need to watch for any talk about double ordering.
Exactly. The risk that customers are ordering the same chip from multiple vendors, creating an artificial demand spike that could crash later.
Policy volatility is the other big swing factor.
Absolutely. Policy headlines drive short-term stock moves. Two things to watch. First, any change to the license approvals for those China legal GPUs from NVIDIA. Second, the pace of CHIPS Act grant announcements for the big projects in Arizona and Ohio.
Given the mixed global economy, is macro softness a risk here?
Not immediately for the leading edge segment, thanks to that massive backlog. High interest rates are a risk, sure, but the backlogs in AI and memory provide a big cushion. Cloud providers keep signaling continued aggressive investment in AI infrastructure no matter what.
Okay, let's transition to the medium term. The 3 to 5 year horizon, so 2026 through 2030. This is the period defined by that structural demand supercycle.
This horizon is underpinned by three massive structural drivers that are pushing the industry toward $1 trillion in annual revenue by the end of the decade. These aren't just cyclical peaks, they are permanent market expansions.
Starting with the fastest growing segment, automotive.
Automotive is transitioning from just a buyer of chips to a technology driver. It's expected to potentially triple its semiconductor market size by 2030. Think about it. An older car might have $500 worth of chips. A level 4 autonomous EV needs upwards of $4,000 worth of silicon.
Wow.
That growth is driven by high-voltage power electronics, the CC and GaN chips, and complex ADAS chips and sensors.
The second driver is the behemoth we've already discussed, AI and cloud computing.
And this juggernaut is not slowing down. By 2028, we'll see more competition in AI silicon. AMD's MI300 and Intel's Gaudi systems are gaining traction. That's great for innovation, but it could start to pressure the margins of the current dominant players.
And finally, the broadening reach of computing, wireless and IoT.
The Internet of Things is a volume game. Billions of new sensors, smart home gadgets, industrial automation, and importantly, most of these use mature node chips, which benefits companies like Texas Instruments and Microchip.
This era is also defined by massive capital deployment, which carries the CapEx overshoot risk.
This is the primary risk to watch between 2026 and 2028. Dozens of new fabs in Arizona, Texas, Ohio are all scheduled to come online. The SIA projects global fab capacity to increase about 56% by 2030. All this front-loaded investment creates a tangible risk of tactical oversupply in certain segments.
And who gets hit hardest if that happens?
The contract manufacturers and memory makers. If demand for, say, 5mm logic normalizes just as all these new fabs start production, utilization rates could drop sharply. That would hit pricing and profitability for foundries like TSMC and Samsung.
What's the crucial competitive shift that defines this medium term? The Intel swing factor.
This is the single most important competitive variable in the industry over the next 5 years. Intel has this audacious roadmap, 5 nodes in 4 years, aiming to reclaim process leadership by 2026 with their Intel 18A node.
What are the stakes if Intel succeeds or fails here?
The stakes couldn't be higher. If Intel succeeds, it restores their competitive position in CPUs, and critically, it validates their new foundry business. This would create a true foundry duopoly, which would be great for every fabless customer.
And if they stumble?
Then TSMC solidifies its dominance, and AMD and NVIDIA extend their massive market share gains. It's a multi-trillion-dollar question for the industry.
Finally, let's look out to the long term, 10+ years ahead, beyond CMOS. This is where physics and economics really force a reinvention.
By 2035, Traditional silicon scaling making transistors smaller will be near its physical limit. The fundamental question is, how do you keep improving compute performance when the cost per transistor is now rising, not falling?
So Moore's law, as we knew it, is dead. What are the new paths to replace it?
Innovation is pivoting hard to architecture and integration. First, 3D integration. We're moving toward true vertical stacking of logic transistors, building up instead of just out.
And what about new materials beyond silicon?
Research is intense there, exploring carbon nanotube FETs and more immediately integrating new materials like gallium nitride onto silicon for specialized functions that silicon can't handle efficiently. The toolkit is opening up.
And beyond the physical materials, the way we do computing is going to have to shift.
Absolutely. Computing becomes highly AI-centric. We expect the rise of neuromorphic chips, which mimic the human brain for huge energy efficiency gains. We'll also see more analog computing and in-memory computing, which perform calculations directly within the memory to save energy.
So energy use becomes a primary strategic driver.
It has to be. By 2035, the energy consumption of data centers and fabs will be under intense scrutiny. The long-term winners will be those who can balance extreme performance with extreme energy efficiency.
So what's the strategic implication here? If pure scaling stops, who holds the power?
The balance of power shifts. Mastery of advanced packaging and heterogeneous integration, the art of connecting all these different specialized chiplets, may soon trump having the absolute smallest transistor. The value moves from pure lithography to system architecture and integration expertise.
Okay, to recap the core thesis from our sources, the semiconductor full stack is defined by these two powerful growth engines, AI and auto, but it's all complicated by severe supply constraints and a forced multi-billion-dollar geopolitical restructuring. Resilience is now the strategic imperative.
And that view gives us insight into where the investment alpha, the outperformance, might be. While stocks like NVIDIA already reflect massive optimism, the potential for outperformance may be in currently undervalued segments that occupy these strategic choke points.
We highlighted two key areas. First, memory.
The market seems to consistently underestimate how tight the DRAM market, especially HBM, may remain. SK Hynix forecasting a shortage into 2027 is a very strong signal. This isn't a short-term blip. It's a structural shift.
So there's room for upside in names like Micron or SK Hynix.
Potentially, yes.
And second, the bottleneck that defines the immediate friction, packaging.
Yes. The back-end and packaging specialists, firms like AE Technology and Amcor, are expected to re-rate higher. They're transitioning from low-margin assemblers into critical high-technology firms. As they expand capacity, they move up the value curve.
And the essential infrastructure?
The equipment and EDA tool giants, ASML, Applied Materials, Synopsys, Cadence, they benefit from that guaranteed multi-year CapEx supercycle driven by the cheap EPS acts. They are foundational, lower volatility plays with the widest moat in the industry.
The semiconductor industry in 10-plus years will look fundamentally different. It's constrained by physics, but it's being reinvented by new architecture and materials. The government support we're seeing isn't short-term. It's a long-term shift to treating this industry almost like a national utility.
Which leads us to our final provocative thought for you, the listener. Given the national security implications and the hundreds of billions in government backing, the question is this. Will future governments prioritize securing the supply chain above maximizing global economic efficiency? And what does that elevated price of sovereignty, those higher operating costs in the US and Europe mean for the ultimate cost of every digital device and cloud service we use?
Will everything simply become structurally more expensive in the name of security? A profound and vital question for our future. That was a deep dive into the semiconductor full stack. We hope you feel thoroughly informed faster.